All right. Hello, everyone. So this week we're going to continue talking about integration. Last time we sort of just briefly reintroduced the idea of Riemann sums, upper and lower Darboux sums, and a little bit about just sort of what are all the definitions we need to construct the idea of integration. And today we're going to sort of carry that on, not only to look at sort of properties of Riemann integrals, but also to look at a different type of integration, which is called Riemann-Stieltjes integration. And I should say that it's actually not a different type of integration so much as Riemann integration, as we normally think of it, is a special case of this other more general type of integration we're going to talk about called Riemann-Stieltjes integration. So if you read the book, which I hope you have done before watching this video, so if you haven't looked at the book yet, I would stop here and go and look at the book first, because what the book does is it defines Riemann integration, and then it works through a bunch of properties of Riemann integration. Then it defines Riemann-Stieltjes integration, and it works through a bunch of properties of that. For the sake of time, I'm actually going to do it a little differently, because as I mentioned, Riemann integration is just a special case of this other type of integration called Riemann-Stieltjes integration. So actually what I'd rather do is I'd rather just go ahead and introduce Riemann-Stieltjes integration, see that Riemann integration is in fact just a special case of Riemann-Stieltjes integration. And then if I prove these things for Riemann-Stieltjes integration, then they'll also follow for Riemann integration. Now we're not going to do that for everything. There'll be some things towards the end where we go back and say, okay, these are special things, or at least maybe we just really want to focus on them in the case of Riemann integration. But there'll be a lot of sort of things we can knock out just by looking at the case of Riemann-Stieltjes integration. So then we don't have to sort of prove things twice. But if you look at the book, it will sort of walk you first through the proof of the statement using Riemann integration, and then we'll introduce Riemann-Stieltjes, and then we'll walk you through the proofs again. So that's sort of a nice way to lay it out in the exposition, I think, but for the sake of our time, I want to sort of just look at Riemann-Stieltjes and prove things for Riemann-Stieltjes integration. All right, so what is Riemann-Stieltjes integration? So I've already written the definition up here. This is the same definition you will find in your book on page, what page is it on here? So it starts on page 81. This is definition 212. So the big difference here is the introduction now of this function alpha. Okay. So I'm going to suppose alpha is a monotonically increasing function on the closed interval AB, and I'm going to let f be a function from AB into R, which is bounded. Now, for the next little bit, it seems the same, right? So I'm going to take a partition of AB. I'm going to call the tags of that partition CK. But now instead of having, right, when we have Riemann integration, I have this delta xk, which was just xk minus 1. But now I have this thing that I'm going to call delta alpha k. And delta alpha k is just alpha of xk minus alpha of xk minus 1. Okay, so I'm replacing this concept from before of delta xk with delta alpha k. Okay. Then, and I'm not going to write, I had to look up how to spell Stieltjes, and I'll have to keep looking it up if I keep writing it. So I'm just going to write capital R dash capital S for Riemann-Stieltjes. So the Riemann-Stieltjes sum of f with respect to this other function alpha is, so we just denote this capital R of Pf, and now because we have this function alpha, it's the Riemann-Stieltjes sum of, with respect to really the partition, the function f and the function alpha, is equal to, and again, you'll notice this looks almost exactly like our Riemann sum, except now instead of a delta xk here, we have a delta alpha k. Okay? So really what Riemann-Stieltjes integration is doing is sort of allowing you to weight different x values differently. Okay? Now there's still properties about this, right? I mean, it has to be monotonically increasing, but it's sort of allowing you to weight different x values differently. So, for example, you might want, if you're looking on the interval 0, 1, right, you could take, or let's say minus 1 to 1, you could take alpha of x to be 0 when x is less than 0, and 1 when x is greater than 1. So that would be a perfectly good monotonically increasing function. And then you could look at sort of what's going to happen here. Essentially, here you're giving sort of no weight to any of the points less than 0. And you might think, oh, I'm giving a lot of weight here. But actually, because you're looking at these delta, you're looking at this delta alpha k, what you'll actually see is that the only partition that ends up counting is one where you switch values, right? Where you go from 0 to 1. So then you would have a 1 here and a 0 here, okay? So the only partition that ends up counting when you're looking at sort of this setup with this particular alpha is the partition that includes 0. Okay? So we'll look at, oops, sorry, I should say when x is greater than 8 or 0. There we go. So we'll look at some examples, and in fact, the book has some nice examples, but let me just sort of point out that we can sort of keep going here, and now we can just generalize all the things we looked at before, but now with respect to this other function alpha. So I can have upper and lower. So before I had upper and lower Darboux sums. Now these would be called upper and lower Darboux-Stieltjes sums. Okay, but they're defined in exactly the same ways, except we replace that delta x sub k with a delta alpha sub k. So my upper sum is just the one where I choose my tags such that on each interval in the partition, I pick the maximum value, right? And then I just have delta alpha k. Lower sum, I choose the minimum value in that interval times delta alpha k. Once I have upper and lower Darboux-Stieltjes sums, I can define upper and lower Riemann-Stieltjes integrals. So the upper Riemann-Stieltjes integral is just the infimum over all partitions of the upper Darboux-Stieltjes sum. Okay. Similarly, the lower Riemann-Stieltjes integral is the supremum over all partitions of the lower Darboux-Stieltjes sums. These become sort of a mouthful to say because you're putting all these names together, but it's exactly the same sort of idea. It's just we're building it up now with this delta alpha k instead of the delta x k. Then, of course, the same sort of definition follows then that we say a function is Riemann-Stieltjes integrable if the upper and lower Riemann-Stieltjes integrals agree. Okay, so if they have the same value. Okay, so again, I said if we look at this, if I choose alpha of x just to be x, okay, so I choose alpha of x to be the identity function, but actually, I'll first note that alpha then is a monotonically increasing function on any interval I want to choose. So that fits my hypothesis here. But now notice that when I come down here, if I choose alpha of x to just be x, then delta alpha k is alpha of x sub k, well, that'll just be x sub k, minus alpha of x sub k minus 1, that'll just be x sub k minus 1. And that's just exactly what we called delta x sub k before. So then here I would have a delta x sub k, delta x sub k, delta x sub k. So all these things go back to the normal case of Riemann integration. So this Riemann-Stieltjes integration idea is really just a generalization of Riemann integration where I sort of allow myself to weight points differently. Okay. All right, so let's then look at a couple of theorems. So sort of a fundamental question once we have these definitions then is like, so if I have a function, right, how do I possibly know whether it's Riemann-Stieltjes integrable? Okay. And so the first theorem we want to look at here is theorem 2.43. So this says a function f is Riemann-Stieltjes integrable if and only if there exists, or sorry, if and only if for every epsilon greater than 0, there exists a partition P such that the upper Darboux-Stieltjes sum minus the lower Darboux-Stieltjes sum can be made less than epsilon. Okay. So, right, the idea here is that, in some sense, the function will be integrable if I can make the upper and if I can choose a partition to make the upper and lower Darboux sums as close as I want. Okay. So let's see how this works. So first, note that it's an if and only if proof. Okay. So let's start sort of in the forward direction. So first, assume F is Riemann-Stieltjes integrable. With respect to, so this WRT stands for with respect to alpha. So let's see, what can I do then? So then there exists partitions I'll call them P2, P1 and P2, so that, well, since it's Riemann-Stieltjes integrable, what does that mean? That means that the I can choose a upper sum that is as close as I would like to the value of the Riemann-Stieltjes integral. Okay, so there exists a partition 1 so that the upper sum over that partition minus the Riemann-Stieltjes integral of f with respect to alpha over AB, I can make that difference as small as I would like. And similarly, I need to do some more erasing over here. And similarly, if I look at the difference between the Riemann-Stieltjes integral of f with respect to alpha and this lower P2, or sorry, this lower sum, P2 f alpha, I can make that less than epsilon over 2. So the idea here is you give me an epsilon, and since this function f is integrable, then I can choose a partition so that my upper sum over this given partition minus the actual value of the Riemann-Stieltjes integral is less than epsilon over 2. And this partition P2, I'll choose so that the difference between the lower sum and the actual value of the integral is less than epsilon over 2. Now notice I've switched these around, right, because we have some ordering, right? The upper sums are always bigger than the actual value of the integral. Lower sums are always smaller than the actual value of the integral. So we have these switched around, but I can basically make sure they're within epsilon over 2 of one another. Okay. Now, you might be tempted here to say, oh, okay, well, if the distance from the upper sum to the actual value of the integral is less than epsilon over 2, and the distance from the value of the integral to the lower sum is less than epsilon over 2, then they must be within epsilon of one another. The only problem is that you have to note that these are actually over different partitions. This is a sum over P1 and this is a sum over P2. If I could say that these things held for a common partition, then I would be done. Okay, and that's exactly what I'm going to do. Okay, so I'm going to let P be the union of P1 and P2, or often we'll refer to this as the common refinement, right? Because these were two different partitions, and then what I'm saying is use all the parts from P1 and the parts from P2 and combine them together to make one big partition. Okay, and since it's a refinement, we know from the last homework that anytime I take a refinement, I get a nice ordering on these things. So in particular, then so the first thing I'll point out here, right, is that if I take a refinement, so this is a refinement of this partition, okay, and since I've taken a refinement, that makes my upper sum smaller. Okay, so since P is now a refinement of P1, then the upper sum will be lower. But let's see, what else do I have? I also have from here, if I just add this integral over here, I have that the upper sum of P1 F alpha is less than epsilon over 2 plus the value of the integral. Okay. But now let me look at this term. If I look here, I can add this to both sides. So I'll add the lower sum to both sides. That gives me that the integral from a to b of f d alpha is less than epsilon over 2 plus the lower sum. So I'm going to come here then. So I'm going to leave the epsilon over 2 alone, but I'm going to plug in something larger than the value of the integral here, and that's epsilon over 2 plus the lower sum of P2 F alpha. Now I'll notice I can combine these two. So combining these two, I get epsilon. And now I've got this lower sum of P2 F alpha, but I'm going to change out P2 for P, which is a refinement of P2. And since P is a refinement of P2, that makes our lower sums larger, right? Refinements make lower sums larger and upper sums smaller. Okay, so I get this. So at the end of the day, what do I have? So UPF alpha, that's here, is less than epsilon plus LPF alpha. Or if I just subtract over, UPF alpha minus LPF alpha is less than epsilon. All right, so I'm halfway done with this proof. What have I shown? I have shown that if my function is Riemann-Stieltjes integrable, then there in fact exists a partition such that the difference between the upper and lower Darboux-Stieltjes sums is less than epsilon. Okay. Now I need to prove the other way around. All right. That was the forward direction. We'll look at the reverse direction now. All right. So now for the reverse direction, assume UPF alpha minus LPF alpha is less than epsilon. Okay, so I'm writing because we're in shorthand here, but let's be careful. So really for any, what we're saying is for any epsilon greater than 0, there is some partition such that this can be made less than epsilon. As you change epsilon, you may have to change that partition also. But given any epsilon, you can always find a partition so that this is satisfied. Now, recall So this really just comes from the definition that, right, we have this nice ordering. I have a lower sum that's going to be less than or equal to the value of the lower integral, which is going to be less than or equal to the value of the upper integral, which is going to be less than or equal to an upper sum. Okay. But if I look at this, then, well, let's see. I certainly know that the difference between these two, between the upper and lower sums, is bounded below by 0, right? The upper sum is always greater than or equal to let me write this out and then talk more. All right, so this one is always greater than or equal to this. So certainly this difference is bounded below by 0. On the other hand, let's see, it's the difference between these two, this minus this, should be smaller than this minus this, right? And so another way to see this is I have a difference. I want to make it larger. So how can I make a difference larger? Well, I can make the top thing bigger. Or I can make the smaller thing smaller. Okay. So I now have that the difference between the upper and lower Riemann-Stieltjes integrals is bounded below by 0 and above by the difference between the upper and lower Darboux-Stieltjes sums. But I know that these are bounded above by epsilon. Yeah, less than epsilon. Okay. So now what have I shown? I've shown that this is trapped between 0 and epsilon for every epsilon. Okay. So that means that the upper and lower actually have to be equal to each other. So this thing then has to be equal to 0. And the only way it can be between 0 and epsilon for every epsilon is if it's in fact 0, equal to 0, because I allow that possibility down here. And if that's equal to 0, then that means these two are equal. And if the upper and lower Riemann-Stieltjes integrals are equal, then it's Riemann-Stieltjes integrable, and the value of the Riemann-Stieltjes integral is just that. Okay. All right. Again, notice that this now tells us, we could go back and say, rewrite this theorem to say a function f is Riemann integrable if and only if there exists a partition such that UPF minus LPF is less than epsilon, right? Because this is just Riemann integration is just a special case of Riemann-Stieltjes integration. Okay? And again, if you go in your book, they'll actually prove that as a standalone result before they do the Riemann-Stieltjes case. Okay. So this is nice, and it's actually really handy to work with. So we'll see the next proof we'll do is going to use this, but it is a little problematic in that it doesn't sort of nicely describe a set of functions that are Riemann-Stieltjes integrable. Okay, so it'd be really nice to be able to say, right, like these particular functions are Riemann-Stieltjes integrable, and so let's do that. Right, and I'm actually also having a small technical issue with my iPad, so let me pause this quickly and I'll be back in a second. All right, sorry about that. So I'm back now. So again, we want to sort of look now at can we say something about like a particular class of functions that are Riemann-Stieltjes integrable. And so the theorem I want then is if f is continuous on the interval AB, then f is Riemann-Stieltjes integrable. Okay. So first, let me point out this is one directional, right? This says if f is continuous on AB, then f is Riemann-Stieltjes integrable. The sort of other direction, if f is Riemann-Stieltjes integrable, then f is continuous, is false. You can certainly find examples of this, and I think there's even some examples in the book where you actually see that in certain cases discontinuities in f don't sort of make your function so bad that you're no longer Riemann-Stieltjes integrable. But if you are continuous, that is sufficient to conclude that that you are Riemann-Stieltjes integrable. I'm also going to point out that so the book actually states and improves this theorem. It's theorem 2.37, but they only do it for Riemann integration. So again, hopefully you've looked at that and tried to make sense of that. We're going to do it in the case of Riemann-Stieltjes integration, and you'll see that actually the proof is fairly similar. We just have to make some small adjustments here or there. Okay, so let's prove this. So here's the proof. So it's all good analysis proofs. Let me start with epsilon greater than 0. All right. So I have this function, and all I know is that it's continuous. But since it's continuous, since f is continuous on AB, I'm going to choose delta greater than 0 so that f of for any x1, x2 in AB with x1 minus x2 less than delta, we have that f of x1 minus f of x2 is less than epsilon. Okay. Now this, if you go back and look at our definition of continuity, we talked about continuous at a point. This is actually slightly different, and in fact, this actually is using something that we haven't totally talked about yet, or at least in as much detail as we will in a bit, which is uniform continuity. So it turns out that if your function is continuous on a closed interval AB, it's actually uniformly continuous on that interval. And really, this is a statement of exactly what that means, right? So this just means that you can take any 2 points in your interval, and as long as you pick those 2 points close enough together, your function values can't be too far apart. So really what this is saying is sort of the delta doesn't depend on your, or you can choose a delta independent of the points you're looking at, right? So like the delta doesn't care where this x1 and x2 are as long as they are close enough together. Okay, so that's really what this is saying. Okay, but we need this. Oh, sorry, and here, I don't want this less than epsilon. I'm going to want this less than epsilon over alpha b minus alpha a. If you're looking at the proof for the Riemann case, that's where alpha of x is equal to x, so this would just be b minus a. But in the case of Riemann-Stieltjes, we can put alpha of b minus alpha of a. Okay, and we'll see why that's exactly the right thing we're going to need in a minute. All right, so now I'm going to choose a partition choose a partition P with the norm of that partition less than delta. So remember, the norm of the partition is just the largest difference between two x values. Okay, so I want here the largest difference between two x values to be smaller than delta. And right, I won't, that way I know my difference between x values will always satisfy this. So the difference between two of my output values will always be less than this. Okay, so that's going to be important. All right, so now that I have this, then what can I say? Well, I want to show that this thing is Riemann-Stieltjes integrable. And our last result, right, was to say that, well, I know it's Riemann-Stieltjes integrable if I can make the difference between my upper and lower Darboux-Stieltjes sums less than epsilon. Okay. So my goal is now going to be to show I can make the difference between these two less than epsilon. That then, by our previous result, implies that the function is Riemann-Stieltjes integrable. Okay. All right. Well, before I need to do some work to get there. So what do I know about this? Well, I can first just write out sort of what these are, right? So the upper sum over this partition would just be this. And the lower sum would be this. Oh, sorry, delta alpha k, delta alpha k. And so I can collapse these. M sub k, capital M sub k minus little m sub k times delta alpha k. All right. Now, remember what these are, right? This capital M sub k is the maximum value on the interval xk minus 1 to xk. The little m sub k is the minimum value on that interval. By the extreme value theorem, I actually know that both of these values are achieved somewhere in that interval. So I can actually write this as, say, f of some value, I'll call it, let's see, to be consistent with the book's notation, I'll call this x k1. All right, so here what I'm doing is I'm just saying there is some x value, which I'm calling x sub k comma 1, where the maximum value of the function is achieved on the interval xk minus 1 to xk. There's some x value x sub k comma 2, where the minimum value of the function is achieved on the interval xk minus 1 to xk. I'm just sort of putting these here. Okay. But this is so let me look at these. I don't want to explore this difference. Well, since, which right, it's over here, since xk1 and xk2 are both in the same interval, I'm running up on that. So they're both in the same interval, xk minus 1 to xk, and since the norm of my partition is less than delta, what does that mean? The norm of the partition being less than delta means every interval of this form is less than delta in length. So since this interval is less than delta in length, and these two come from the same interval, I know that xk1 minus xk2, the difference between those two must be less than delta. Okay. But since the difference between these two is less than delta, then the difference between their outputs must be less than this value. Okay. So f of xk1 minus f of xk2 must be less than epsilon over that stuff. Okay, so that's what I'm going to use here then. So this I can make less than, actually, yeah, I need to put a less in there, less than or equal to epsilon over alpha b minus alpha a times delta alpha k. All right, I'm almost done here. And I'm just going to sort of continue this string of inequalities I have going here. So if I look at this, that's actually equal to, so this expression here is equal to, I could just pull out epsilon over alpha b minus alpha a, because it's independent of k now. Okay, and I get this. And now this is where it might take a little thought, but if you actually write out the values here, this sum is a telescoping sum. So if I write out what this is, right, this is just delta alpha 1 plus delta alpha 2 plus all the way up to delta. Okay. But if you actually go out and write out what each of these is, all right, alpha 1 is alpha 1 minus alpha 0. Alpha of x1 minus alpha of x0. So that's that one. This one is alpha of x2 minus alpha of x1. Okay, and you keep going. What you'll notice is you have this telescoping property. So I'm going to get an alpha x1 here and a minus alpha x1 here. If I wrote out the next one, I would have alpha x3 minus alpha x2. So the alpha x2 would cancel with a minus alpha x2 over here. So this would continue. You notice here you're left with a minus alpha x0, but x0 is a. In the very last term, you would have an alpha xn that wouldn't get canceled with anything. Okay. So you would end up with this sum telescoping to alpha of xn, which is just b, minus alpha of x0, which is just a. And now, okay, we started over here, and what do we get? We showed that the upper Darboux-Stieltjes sum minus the lower Darboux-Stieltjes sum, after a whole bunch of work, is less than epsilon. Okay. And since it's less than epsilon, F is Riemann-Stieltjes integral, and by our previous result. Okay. So now we can at least say, I know that every continuous function is Riemann-Stieltjes integrable. Okay, that's sort of a nice property to have, right? And at least continuous functions, right, are a nice class of functions. So it's nice to know that they at least sort of all have this nice property. You'll see if you're looking just back in the Riemann integrable section, you'll see that there's also this theorem that says if your function is monotone on AB, then your function is Riemann integrable on AB. In one of the homework problems, I'm going to have you explore sort of trying to extend that result to Riemann-Stieltjes integration. Okay, so we're not going to do that here, but I'll have you sort of explore that in the homework and see sort of, are those conditions enough? Can you say that if a function is if a function is monotone on AB, then it necessarily must be Riemann-Stieltjes integrable? So is that true? And if not, are there additional conditions that are needed to make that true? Okay. The sort of other thing I want to point out, you have all these properties again, and again, this is going to be sort of a homework problem I'm going to give you. You have all these sort of algebraic properties of Riemann and Riemann-Stieltjes integrals. So the thing I'll point out there is that, right, if I take two Riemann-Stieltjes integrable functions and add or subtract them, then I'll get another Riemann-Stieltjes integrable function. Okay, so that's easy. However, normally when we've written out these sort of algebra of whatever, right, the algebra of continuity, algebra of limits, algebra of derivatives, we've also been able to say that if two functions have a certain property, that their product has it. But with integration, we can no longer say that, right? And we've actually looked at before counter examples of this, right? So, for example, well, if you take a function like the integral of 1 over x from, sorry, if you take, I'm thinking sort of the other way, right? If, so sorry, I've gotten myself twisted around now. But anyway, certainly with division, right, you could take a function like the function 1, the constant function 1 is integrable because it's continuous. The function x is integrable because it's continuous, right? But 1 over x is not going to be integrable in the way that you might like, right? Especially on an interval that includes 0. So there's sort of some things one has to worry about when combining these. So you sort of don't get the most robust properties just from looking at the algebra of these things, but you do get some nice properties, and I'll ask you to prove one of them in the homework. Okay, but you should go through and convince yourself that like you could reasonably prove all of them. They all really just come down to playing with the definition. The last result that I want to prove for today is one that, again, is very important to calculus. And this is going to be one for which we're going to go back when we're only going to look at the case of Riemann integration. And so this result is the fundamental theorem of calculus. So if you're looking at the book, this is theorem 242. Okay. And so this says if capital F is differentiable on an interval AB, then the integral from A to B of f of x, oh, sorry, and the derivative of capital F is equal to this function little f, which is, sorry, integrable on AB, then the integral from A to B of f of x dx is equal to capital F of B minus capital F of A. Okay. And so again, I mean, I'll sort of point out, I mean, as many of you may be thinking about sort of, you know, your own classes that you're teaching or classes you might be teaching in the future. Unfortunately, right, this sort of gets lost, and I think students in a Calc 2 class often sort of think this is the definition of integration, right? They get tricked into this idea that they sort of conflate integrals with antiderivatives. And I mean, for good reason, right? I mean, the fundamental theorem of calculus tells us essentially that they are related to one another, or that at least we can use antiderivatives to find the value of integrals. But there's sort of a lot of conditions here, right, we have to be careful of, right? In particular, right, this only works if your function f is integrable. Now, in a calculus class, what are we normally working with? Continuous functions. So if I'm working with a continuous function, then I know that a continuous function is Riemann integrable. So I already know it's integrable. And I just find this function f so that this relationship holds. And then, okay, things just come out for free. Okay. But I mean, again, it's one of these things that I think gets lost easily in a class like Calculus 1 or 2 when you're normally talking about this, because very quickly they're just immediately using this to compute a bunch of integrals. Okay, but it's important to note that, right, it really is just saying that this function capital F needs to be differentiable and this function little f needs to be integrable in order for this to hold. Okay, all right, so let's prove this. So maybe I'll just start over here. All right, so let P be a partition of my interval AB. So I'm just choosing the partition now. I'm going to choose my tags of my partition in a very particular way. So I'm going to choose tags, which I'm going to call T sub k, so that capital F of xk minus capital F of x sub k minus 1 is equal to capital F prime of tk times xk minus 1. So actually, let me say, I'm going to choose tk, right, is going to be in the interval, open interval, x sub k minus 1 to xk. Okay. So you might wonder why I can do this, right? I can do this by the mean value theorem. Really what I'm doing is I'm saying choose tk so that f prime of tk is equal to f of xk minus f of xk minus 1 all over, if I divided this over here, xk minus 1. So I can do this by the mean value theorem. Okay, I can choose my tags in this particular way. Okay. But notice that capital F prime is just little f. And this thing here is just delta xk. Okay, so that's going to be very helpful for us momentarily. Okay. So now, given an epsilon greater than 0, I can choose my partition P so that the sum k equals 1 to n of f of tk times delta xk minus the integral from a to b of f of x dx is less than epsilon. So what is this? Why is this true? This is because my function is Riemann integrable, right? So my function is Riemann integrable. I can choose a partition so that I can make any Riemann sum over that partition minus the integral as close as I would like. Okay. So this follows from the integrability. Right. But now I want to note that this statement up here was true for any partition, right? So I can take this and substitute here for this. So this is actually sum from k equals 1 to n. So I'm going to replace this with f of xk minus f of xk minus 1. Okay, so I've just replaced that with that from this previous sort of observation. Okay, so again, it was my very special choice of tags here, the way I'm choosing my tags. Given a particular partition, I'm going to choose my tags in this way. And so I choose my partition so that this works, but also choose my tags in this way so that I get this. Okay. But then what happens? Well, if I look at this sum, this is again a telescoping sum. So just like we did in the last problem, write out the terms and you'll see that that sum collapses to capital F of B minus capital F of A. And then I also have minus this integral. But now what is it saying? It's saying that the difference between these two quantities that I've underlined in green can be made less than epsilon for any epsilon. So given any epsilon greater than 0, I can make these two quantities closer than epsilon. Well, the only way that's true is if this whole thing is equal to 0. This implies not P, sorry, F of B minus F of A is equal to the integral from A to B of F of X dx. And I'm done. All right. So the sort of clever trick here, right, was choosing sort of to choose these tags in the particular way. Now, what would the problem be if we tried to do this for Riemann-Stieltjes integration? Well, the way I wrote this out here and applied the mean value theorem, I get a delta x sub k here, not a delta alpha k. Okay. So with Riemann-Stieltjes, you're going to have a big problem there because it's not quite going to give you what you need for Riemann-Stieltjes integration. So that's why we do this just for Riemann integration. Okay. All right. So we're going to stop the video there. There are some other theorems that, again, we'll explore some of them in the exercise set. But this has been sort of the big picture main ideas of Riemann and Riemann-Stieltjes integration. And so if you have, you can read sort of, there's some additional examples in the book we didn't talk about, a couple of sort of results we didn't talk about either because we're going to talk about them in the exercise set and have you explore them there, or some of them just, quite frankly, I don't find to be that particularly useful. And so we just won't discuss those. But there are a lot of nice sort of examples to play around with there.